Hello students, this is Narendra Kumar Dwivedi welcoming you all once again in today's session. Today we will be starting the session with first topic written on the board as energy stored in a capacitor. When a capacitor is charged from its uncharged position or is fed to an electric potential difference or EMF source, then how the charging process takes place, that we have covered in the previous lecture. Now it's time to see what amount of energy is stored between the plates of capacitor when it is applied to a potential difference. Now to start with, we will be assuming the case that capacitor is fully uncharged. Now let's first define what is the energy stored in a capacitor. So basically the energy stored in a capacitor is the amount of work done in charging the capacitor to a certain potential. So let's calculate. So before that, suppose at any instant we give a charge Q to the plates of capacitor and the potential at that instant on the between the plates of capacitor is V. So Q is written as Q equals to C into small v, potential difference at that moment. Now let a small amount of additional charge dq is supplied to the plate. Then what amount of work is done, let us calculate. Now let an additional charge dq is transferred from negative plate to the positive plate. Then the small amount of work done is. So how do we write work done? So that work done will be equals to dW equals to V into dQ. This is from the very basic definition of electric potential. Now we will be placing the value of V right from here as Q by C. So here we have Q by C into dQ with us. Now as we just integrate both the sides, so the total work done in charging the capacitor to charge, say, capital Q from its uncharged position, that is from 0, can be calculated on integrating both the sides by taking proper limits. So let's proceed. The total work done in transferring charge capital Q is W equal to integral from 0 to Q. This is the limit of Q at uncharged position, no charges, 0, and when it is charged to Q charge, a final amount of charge, then final limit Q upon C dQ. Now let's, as C will be constant, so let's take this 1 upon C out of the integration. So now W is equal to 1 upon C integral from 0 to Q dQ. Now here we have 1 upon 2C Q square. Our limits would be from 0 to Q. Now placing the limit, we'll be having Q square upon 2C as the work done, and this will be the energy stored. So here, let us rewrite this energy stored to be U. So U equals to Q square upon 2C. This is one form. Now, since we have Q equals to CV, so here we can write this U to be equals to C into C square V square upon 2C. So one C will get cancelled. So the next form with us is half CV square. This is another form. Else you can write or U equals to, here you can write half C into V. So this is Q. So half Q into V as your next form. Okay, now let's see the graphical method. How do we obtain the previously obtained results using graph drawn between charge and electric potential? So let's proceed with graphical method. Graphical method. So to begin with this, since we have Q equals to CV, as C is constant, therefore Q is proportional to V. It means if we draw the graph between electric charge and electric potential, so that will be a straight line. So let's draw that graph first. Suppose this is y-axis, two-dimensional coordinate system we are having, 0. On x-axis we are representing charge Q, and on y-axis electric potential V is being represented. So the graph would appear to be a straight line as this equation suggests. So let this point be A, and let's draw a perpendicular right from this A point on x-axis, and the point, let me call it as B. So directly let's calculate the area bounded by this VQ graph with Q axis. So area of triangle OBA, that is equal to half base into height. So base would be OB, height would be BA. So this is equal to half. Now this actually this area would represent the electric potential, the electric energy stored or energy stored in a capacitor. So base is Q and this BA is V. So half QV, and this we are writing it as U. Now for the next form of this, we can write half Q equals to CV, this relationship we are having with us, into this V. So this is half CV square, next form with us. Now or you can write U equals to, for this V you can have Q by C from there. It is half Q into Q by C for V. So this is Q square upon 2C. So these are forms getting obtained with the help of. So now let's have next topic, energy stored in series and parallel combination of capacitors. So here basically what we will be assuming or proceeding with, we will be having first series combination of n identical capacitors, and later on those n identical capacitors will be connected in parallel, and in these two types of combinations, what kind of energy or how the energy stored in such combinations gets calculated, that will be seen here. So let's proceed with first series combination. So in case of series combination, it is the charge that remains constant between the plates of all capacitors connected in series combination. So here we will be writing that electric or energy stored U equals to Q square upon 2C. So here this will be further written as equals to Q square upon 2 into 1 upon C. Now what upon 1 upon C? C is what? C is the capacitance of that capacitor, which is the equivalent capacitor representing the series combination of n capacitors having capacities C1, C2, C3 and Cn respectively. So this 1 upon C will be written as 1 upon C1 plus 1 upon C2 plus dash 1 upon Cn. So this is 1 upon C value representing the series combination. Now further we can write this as we just multiply this Q square upon 2C1, this will be the energy of first capacitor in the combination. So I am writing it U1 plus the second term representing energy stored in second capacitor. So likewise this is Un, energy stored in nth capacitor in the series combination. So this way we can calculate energy stored in case of series combination. So let's proceed with parallel combination. So again we have those n capacitors getting now connected in parallel. So in case of parallel combination, what remains constant across all capacitors in combination, that is the electric potential. So here we will be using the form U equals to half C into V square. Now this C is what? C is the capacitance of the equivalent capacitor representing the parallel combination of n number of capacitors having capacities C1, C2, C3 dash Cn respectively. So let's write this C half V square into, for this we can write C1 plus C2 plus Cn. So this way, this is the equivalent capacitance of parallel combination of n capacitors. Now as we multiply this term, so this will give us half C1 V square, that is the energy stored in first capacitor in parallel combination. So I am writing it as U1 plus this half C2 V square will be the energy stored in second capacitor in parallel combination. So likewise this is Un. So this is how we can. Next topic with us, and that's energy density in parallel plate capacitor. So to begin with this topic, let's first define it. What is energy density in parallel plate capacitor? It is basically the amount of energy stored per unit volume of capacitor. So this is the energy density, and with this definition we will be proceeding. So here suppose Q, since we have Q equals to A into sigma, where the sigma is surface charge density of plates of capacitor. So sigma will be equals to Q by A, and as we have on cross multiplication, Q equals to A into sigma. Now this sigma will be written as equals to epsilon naught into E. So this further is written as A into epsilon naught into E, as the electric field intensity between the plates of capacitor or in the region bounded by two parallel plates will be sigma upon epsilon naught, equal to sigma upon epsilon naught. From there, on cross multiplying epsilon naught, we have sigma as epsilon naught into E with us. Now further, we can write it the value of C with us as, here we can write, since C equals to epsilon naught A by D. So this is the capacitance of capacitor. C equals to epsilon naught A by U equals to energy with us as Q square upon 2C. So here we can write the form of Q as equals to A epsilon naught E, and thereby for this C we can have this form. So this is A square epsilon naught square E square upon 2 into C. For C I am writing epsilon naught A by D. So this is the value of Q right from this equation, and for this C we are having this. Now epsilon naught will get cancelled with this square, and A also will get cancelled with this square, giving us finally it's D into, this D goes up, so this is A into D epsilon naught half epsilon naught E square, like this. So A into D is what? Volume. So the energy density, small u equals to capital U upon AD, and which is equals to half epsilon naught E square. So now let's have next topic with us, redistribution of charges and concept of common potential. Here actually we will be having two capacitors, two conductors having different charges at different potentials. Now when these two conductors having different capacity, different potential, different charges will be joined through a wire, a conducting wire, then the charges will start distributing, and those charges will be transferred from a conductor which is at higher potential to the conductor at lower potential, and this distribution of charge continues so long as both conductors are at same potential, and that same potential, constant potential, which is necessary or which shows the steady condition of distribution of charges, and at that particular potential value the distribution of charge between the conductors gets obstructed, gets stopped, and steady state condition is said to be attained. So let's proceed to calculate that common potential. So here to begin with, let me have two conductors with us, namely say A and B. Suppose this is conductor A and this is conductor B, and we are having these two conductors placed on an insulating stand so that there is no contact with the surface on which it is kept and no leakage of charges condition may take place. Now say this conductor A is having Q1 charge, is at P1 potential and having C1 capacity. Likewise, conductor B is having Q2 charge, having C2 capacity and is at V2 electric potential. Now suppose these two are joined through connecting wire, and through this the charges start transferring. So here, to begin with, let we have common potential V equals to, how do we write common potential? V equals to Q, total charge upon capacity. So Q equals to total charge upon total capacitance. Okay, now what's the total charge? It's Q1 plus Q2 upon, say it is C1 plus C2 as the total capacity. Now for this Q1 we can have C1 V1 with us. For this Q2 we can have C2 V2 with us. So we write now common potential as V equals to C1 V1 plus C2 V2 upon C1 plus C2. So this is the common potential with us. Now let's calculate the value of charges after redistribution. So now the charges after redistribution, let me call the first charge in first conductor Q1 dash equal to C1 into V, as the potential will be common. So here we can have this V value, let me call this equation number 1, and Q2 dash will be equals to C2 into common potential V. So let's have now the ratio. So Q1 dash upon Q2 dash, which is equal to C1 upon C2. Okay, so now let's have next topic with us, loss of energy in redistribution of charges. As in the previous topic, we had common concept of common potential and redistribution of charges. So this topic is just in connection to that previous topic. When charges are transferred between two conductors or two conductors at different potentials, then they are transferred through connecting wire. So connecting wire offers certain resistance to those charges, and due to that hindrance, because of that hindrance, the amount of work is done which is obtained in the form of heat on the connecting wire, and the connecting wire gets heated, or ultimately we can say there is loss in electrical energy, and that loss in electrical energy is found in the form of heat or thermal energy across the connecting wire. So let's calculate how much or what amount of loss is seen during the redistribution of charges. So to begin with this, let we have energy before connection. connection. That means when two conductors are not connected together, that time total potential energy U, let me call this UI, initial potential energy, and this is equals to half C1 V1 square plus half C2 V2 square. Let this we call equation number 1. Now, similarly we write the energy after connection. After connection, that means when both conductors are now joined through connecting wire, so the total potential energy again we are writing UF, final total energy, it will be half the total capacitance, half C1 plus C2 into common potential they will be attaining. Let me call this equation number 2. So let's directly calculate the value of UF as half C1 plus C2 with us. Now common potential also we can place as we obtained in the previous topic. So this would be C1 V1 plus C2 V2 upon C1 plus C2 and its square. Don't call this equation number 2 right now. Let's simplify this. So on simplification you can have the C1 plus C2 getting cancelled. So there's half into C1 V1 plus C2 V2 square upon C1 plus C2. Now you call this to be equation number 2. Okay, now let's calculate the loss. So the loss in energy will be UI minus UF. Let me call this to be delta U, and this will give us half this first equation C1 V1 square plus half C2 V2 square minus this second equation, half into C1 V1 plus C2 V2 square upon C1 plus C2. So let's simplify this. Now on simplification you will be getting C1 into C2 upon 2 C1 plus C2 into V1 minus V2 square. So this will be obtained after simplification. As can be seen, this UI minus UF is greater than 0. That means it is a positive term. So clearly it indicates that there is loss in potential energy. Now that loss in potential energy is obtained in the form of heat. Now suppose we have C1 equals to C2 equals to C, or both conductors are of same capacity which are joined through the wire. In that case, let's see what's the value of that loss in energy, and it is 1 by 4, right from this, 2C, 2 to the 4th C, and that C will get cancelled from 1C at numerator into C into V1 minus V2 square. Okay, now let's have few numericals. So the very first question, it has got two parts. The first part, find the equivalent capacitance between A and B in the combination given below. Each capacitor is of 2 microfarad capacitance. Now the diagram is there. I'll be drawing on the board. Second, if a DC source of 7 volt is connected across AB, how much charge is drawn from the source and what is the energy stored in the network? Charge and energy both are to be calculated in the second part. So let's begin the first question. For the first part, we have a network given in the question, point A. Now capacitor of capacity says C1. Second capacitor of capacity C2. Third of capacity C3. Fourth of capacity C4, and the last C5 capacitor, point B. Now here it is point P, here it is point R, here it is point S. So P and S both are connected. And here it is point T. So R and T are connected. So as can be seen, now this C2, C3 and C4, these three are in parallel connection. As this is connected here, now this is connected here. So this makes such connection is parallel one. So here, to start with, we'll be writing since C2, C3 and C4 are in parallel, therefore CP we are calculating, it will be C2 plus C3 plus C4. As all capacitors are of capacity 2 microfarad, so 2 plus 2 plus 2, that makes 6 microfarad as the capacitance. Now, as can be seen, between this P and T, if we have a capacitor of capacity 6 microfarad, so that is in series connection with the C1 and C5. So now we write, now C1, CP and C5 are in series, therefore 1 upon CS equal to 1 upon C1 plus 1 upon CP plus 1 upon C5. So here we will be having 1 upon 2 plus 1 upon 6 plus 1 upon 2. So just having simplification to this, you will be having 7 by 6, or else you can write CS equal to 6 by 7 microfarad, or this you can write 0.86 microfarad. So this is the first part of the question. Now for the second part of the question is saying if we connect A and B with 7 volt potential, then how much charge is drawn and what is the energy stored in the network, that needs to be calculated. Now for that we just begin to calculate the charge first. What amount of charge is drawn? Yeah. So this is Q equals to C of equivalent into V. So this CS we got as 6 by 7 and 7 volt potential is applied. So this gives 6 microcoulomb of charge. Now the second part, energy, is also to be calculated. So U equals to half Q into V. So here we write half, charge is 6 into potential is 7. So 21 microjoule is the question. Keeping the voltage of the charging source constant, what would be the percentage change in the energy stored in a parallel plate capacitor if the separation between its plates were to be decreased by 10%? So initially whatsoever may be the separation between the plates, now that has decreased by 10%. At that moment, what is the percentage change in energy stored that needs to be calculated? So let's begin with question number 2. So here we write, since U equals to half CV square, or which is equals to half its epsilon naught A by D as the capacity into this V square, and U2, let we call this to be U1. As can be seen here, only everything will remain same except this D. So you can write U proportional to D. You can write inversely proportional, sorry. U is proportional to 1 by D, we can write. Rest of the things are constant for the next case as well. So here, therefore, we can write U2 upon U1, that will be equals to D1 upon D2, and this is equals to 100 by 90, which is equals to 10 by 9. Now, just subtracting 1 from both the sides, we have U2 upon U1 minus 1, which is equals to 10 by 9 minus 1, and this gives us 1 upon 9, and here we have delta U upon U1. Now multiplying both the sides by 100 to have the percentage change, 100% into 100, so this gives us 11.1%. Okay, now let's have next question. Two capacitors of unknown capacitances C1 and C2 are connected first in series and then in parallel across a battery of 100 volt. If the energy stored in the two combinations is, that means in series and later on in parallel, 0.045 joule and 0.25 joule respectively, determine the values of C1 and C2. Also calculate the charge on each capacitor in parallel combination. So let's begin. Question number 3. So here, first let's have, in case of series combination, in series we have energy U equals to 0.045 joule. So energy U equals to C1 C2 in case of series upon 2 C1 plus C2 into V1 minus V2 square. What is the potential difference? It is given in question as 100 volt. Yeah, 100 square. So let this be solved to give us the value of C1 into C2 upon C1 plus C2. So this will give us, on solving, 0.09 into 10 powers to minus 4. Let this be equation number 1. Now let's proceed for parallel combination. In parallel, we have energy given in question to be 0.25 joule, which is equals to half C1 plus C2 into V square. That V is again given to be the same 100 square. So let's solve for the C1 plus C2 value. So C1 plus C2 will be equals to 0.5 into 10 powers to minus 4. Equation number, let me call equation number this to be 2. Now, as we place this value here back, we can have C1, C2. So let's proceed. Now, from first C1 C2, which is equals to C1 plus C2 into 0.09 into 10 past to minus 4. Now placing this value, we have this C1 into C2 is equal to 0.045 into 10 past to minus 8. Let this be called as equation number 3 it is. Now let's calculate the value of C1 minus C2 so that we can add this equation with that C1 minus C2 value to have the value of C1 and later on C2. So now we can have C1 minus C2 square equals to C1 plus C2 square minus 4 C1 C2 with us. Now we have the value of C1 plus C2, we have the value of C1 C2. So just placing these values here, we have 0.5 into 10 past to minus 4 square minus 4 into 0.045 into 10 past to minus 8. So this is the value of this. Now on solving this and taking the square root on both the sides, you'll be having the value of C1 minus C2 is equals to 0.26 into 10 past to minus 4. Now this equation we are calling equation number 4. So this is the value of C1 minus C2. Now we can add this 4 and 2 from second and fourth. We have this 2C1 which is equals to 2C1 which is equals to 0.76 into 10 past to minus 4, or C1 to be equals to 0.38 into 10 past to minus 4 farad, and as we just place this value back in that equation or in this equation, we get the value of C2 to be 0.12 into 10 past to minus 4 farad. Let's have the second part of the question. Now also calculate the charge on each capacitor in parallel combination. So the charges, for charges you can write Q1 equals to C1 into V, and C1 we have 0.38 into 10 past to minus 4 into 100 volt, or you can write 10 past to 2. So this is 0.38 into 10 past to minus 2 coulomb, and later on you can have Q2 equals to C2 into V. C2 we have 0.12 into 10 past to minus 4 into 10 past to 2. So this is 0.12 into 10 past to minus 2 coulomb. Let's have next question. A 5 microfarad capacitor is charged by a 100 volt supply. It is then disconnected from the supply and is connected to another uncharged 3 microfarad capacitor. How much electrostatic energy of the first capacitor is lost in the form of heat and electromagnetic radiation in the process of attaining the steady situation? Here actually the first capacitor of capacity 5 microfarad is charged using the potential of 100 volt supply. Now it is disconnected and is further connected with another next capacitor of capacity 3 microfarad. So obviously the 3 microfarad capacitor is at 0 potential and 5 microfarad capacitor is having 100 volt potential. So now due to the potential difference across the connection, charges will start redistributing, and this redistribution will continue so long as there is a common potential across both capacitors 4, 5 and 3. At that particular stage, the steady situation is reached and we need to calculate what amount of energy is lost. So let's start. Question number 4, it is, so we now calculate first U1, it's half CV square and C is 5 micro, 10 powers to minus 6 into V square, that means 100 square, so directly I am writing 10 powers to 4, so this will give us 2.5 into 10 powers to minus 2 joule. Now let's calculate the common potential value. So common potential V equals to C1 V1. So C1 into V1 plus C2 into V2. V2 is zero potential across 3 microfarad upon C1 plus C2. So on solving this, we'll be getting 125 by 2 volt. Now let's calculate U2. So U2 will be equals to half C1 plus C2 into V square. So C1 plus C2, 5 plus 3, that's 8 microfarad, 10 powers to minus 6 in farad, into common potential V square, so 125 upon 2 square. So as we just solve it, we will be getting 1.56 into 10 powers to minus 2 joule. So this is initial potential energy and this is final potential energy. Now let's calculate the loss. Now the loss delta U equals to U1 minus U2 and this is equals to 2.5 minus 1.56 into what's common, 10 powers to minus 2. So this on simplification will give us 0.94 into 10 powers to minus 2 joule. So students, with this we end up today's session. Do like and subscribe the channel.